Is it the corner of the window?
Why is this happening? Okay, so, like I said, we're talking about polynomials. So the first thing we're talking about is whether it's continuous. Okay, it's continuous if none of the following things occur. Okay, and I drew you little pictures underneath for each. Okay, so no breaks. There's no break in our graph. We don't have any holes. That's what the open circle stands for. And there's no gaps. This is an example of a gap when we had two different graph lines happening. This was our rational function. There was that vertical asymptote there. Okay? So if any of those three things happen, we say our graph is not continuous. Today, we're going to focus only on ones that are continuous, which is all polynomials. So that's a pretty powerful statement. All polynomials are continuous. Okay, so everything that we look at today will be continuous. We just have to cover that definition right off the bat. Okay, you probably won't hear me use this word the rest of today. But we have to throw it in somewhere because it's in our curriculum. Okay? These two graphs over on the side are examples of what continuous ones look like. The bottom, you already drew these pictures. The only one you didn't draw is this absolute value function. Okay? This has a cusp right there. It's not a nice curve. Okay? So there's a difference there. So that is not a polynomial. Okay? We've seen that graph a bunch before. I just threw it in there one last time. All right. Power functions. Okay? Power functions. We see powers come into play when we think about our degree, right? So our power functions, power is another word for exponent, right? Or the highest degree. So,
Is that like an N?
it's an N. Yeah, it's a letter N.
What?
It's a little cursive N. Does that not look like an N to you? You should see your handwriting, sir. Okay. Okay, so here's the little rule here. So when N is even, when my exponent is even, the graph is going to be similar to x squared. Now we know what that looks like. Okay, x squared is our parabola, so it's this or that. Okay, so it's going to be similar to that. If my exponent is odd, so for example, it's going to be similar to x cubed, which we know looks like that. Okay? Again, we've talked about all this. None of this is new. Okay? We're just refreshing ourselves, all getting on the same page. The greater the value of n, the flatter the graph is near the origin. We'll see what that looks like on the next page. Okay? The greater the exponent, the flatter my graph is at the origin. Okay? And we'll draw this picture. You have some pictures actually off to the side there. We're going to draw some on the next page. Okay? Yep. All right. Okay. So again, here's your picture. See how it's getting flatter around the origin? That's what we mean by that, when the n value goes up. All right, can I move now?
Yes.
Okay. All right, so here's our first one. We're first going to talk about transformations and how that'll impact our graph. But then we're actually going to move away from transformations at the end of our lesson today. Okay? So look at A. When I look at A, the first thing I want to look at is my power, or my highest degree. Okay? So I have a 5. That's an odd number, so I know it's going to be similar to which kind of graph? Yeah, the cubic one. Okay? So I know it's going to be similar to that one. Okay? I know it's similar to that, so it's going to look something like that. Now, look at that negative value. Okay, so you think it's going to go down. What does a negative out front tell me in transformations? What did that stand for? A reflection. Perfect. That told me a reflection. Okay, so if it's similar to this, but I'm reflecting it, it's going to look something like that. Okay, we just reflect it. Okay, now,
whatever that means.
so reflecting it, all I did was I took this and I reflected it. That's how I knew it turned into that way. Now the 5, that's a pretty high value. So I also know that in my graph, it's going to be pretty flat here in the middle, more than I was used to. I'm kind of emphasizing it, okay? But that 5 tells me that it's going to be more flat near the origin than if I had an x cubed situation, okay? So that's our power function. All right, any questions on how I graphed this one? Yeah, go.
So if the thing says it's odd, it just goes up to 5?
This, you mean? All that tells me is that it's similar to my x cubed right here. So I knew it had to be this like snake shape. That's all the 5 told me was the about shape it was going to be. Okay? And then because it was higher than 3, I knew it was more flat at the origin. Okay? Good question. All right, let's do B. So I look at B, look at my exponent. It's even, so I know it's going to be similar to what graph? The square one, right? Or my quadratic. So I know it's going to look like that, about. Okay? Now let's talk about transformations for a hot second. I have a +1 inside with the x. What kind of a transformation is that talking about? Horizontal, left 1. Okay? Horizontal, left 1. So, if I start at the origin, so here I'm starting, I'm going to go to the left 1. And now before I draw my graph, again, I know it's going to look like a U. I'm not reflecting it. Okay, so I know it's still going to look like a U. But my 4 is higher than 2, so it's going to be a little flatter at that vertex point. Okay? Again, I'm kind of emphasizing, but notice it's just a little flatter, a little wider down here at the vertex. Because I'm an imperfect person, and hold on. I'll fix it. Is that better?
Yeah.
Okay.
No, it's not bad.
All right. So those are our power functions. Okay? Any questions on B? All right. Let's talk about the leading coefficient test. All right, so just copy this down for a second, then I'm going to talk about our picture, because that's where it'll come into play. The leading coefficient test, I highlighted that because that's the wording you're going to see on the homework, on the test. Okay, we're going to see it on our examples here. You'll see leading coefficient test. Now, leading coefficient test is a fancy way of talking about end behavior. Okay? So end behavior, leading coefficient test, they're talking about the same thing. Okay? Now, it's going to get kind of wordy, so I'll let you copy first, and then I want you to put your pencil down, and I'm going to explain it on the board. Okay, so copy it down first. Sorry, I can't necessarily zoom in anymore, so if you can't see something, ask me, and I'll tell you what it says. Again, if you're a color coding person, notice my colors. Okay, I'm using different colors for a reason. Okay, you need to put that away and write this down. You don't even have this in there. Come on. You're going to use it on your test. All right, so Like I said up here, we're talking about end behavior. So when I say that, I mean the end behavior of our graphs. So what I circled, right? So at the very end, where will my arrows be is kind of what we're talking about when I say end behavior. Okay? Now it's called the leading coefficient test because we're going to use the coefficient out front. Okay? We're going to use the leading coefficient. Okay? Now, what we're about to talk about is all the times when my exponent is odd. Okay, so when my exponent is odd, aka 3, 5, 7, 79, right, all the above. Anytime it's odd, these are the rules we're going to use. Okay, so I'm going to talk about, we'll do positive first. All right, so when A is positive, so when my leading coefficient is a positive number. Yes, sir. Are we out of tissues? I actually have another box. Okay, so when my leading coefficient is a positive number, okay, I know that I start down, so I'm reading my graph left to right, the first thing that happens is it's going down, and then it ends up, okay? And that kind of holds true with our x cubed, right? We had that little snake, it started down and ended up. When A is negative, it reverses. Okay, so when our leading coefficient is a negative number, I'm starting up and ending down. Okay, that's all we just did. Okay, a good rule of thumb, a kind of trick that I use, when it's odd, so when my exponent's odd, I know my end behaviors are in two different directions. Okay, one's up, one's down. If it's positive, it starts down, so it's like opposite of what you'd think. If A is positive, I'm really starting towards the negative direction. If A is negative, I'm really starting toward the positive direction. Okay? All right, here's our next one. Same idea, just with an even exponent. Okay, so when my exponent is even, we still look at our leading coefficient. That still tells us the end behavior. I think that when it's even, it's a little easier to understand. Less things to remember. If my leading coefficient is positive, both end behaviors are pointing up. If A is negative, both end behaviors are pointing down. Makes sense. Okay? And both end behaviors are the same. All right. So again, I know this seems random. We're going to put all this stuff together at the very end. Okay, so just stay with me. Let's practice our end and right behavior. Oh, let me actually pause here. At the bottom, sometimes you'll hear people talk about rising and falling too. I prefer the language it starts down, ends down, or starts up, ends down. Some people will say it falls and rises, okay? Some people will say that language means the same thing, okay? All right, so let's look at number 1 here. My directions say describe the right-handed and left-handed. Just think starting and ending behavior, okay? So for A, I look at my highest degree. I see that it's odd, okay? It's a 3. Right away, I know that I'm going to have 2 different end behaviors. One's going to be up, one's going to be down because it's odd, okay? I have a negative leading coefficient. So because it's a negative leading coefficient, what did we say? What would it be if it was negative first? Yeah, it would start up and down. So in other words, on my graph, I don't know where I am, but I know that I'm starting up, ending down. I have no idea what happens. It could be like this for all I know. I don't know. I don't know what happens in the middle. But I do know that I'm starting The start of my graph is pointing up. The end of my graph is pointing down. Okay? Try B and C. Try B and C. Find my end behavior for those two. All right, so B, I have an even leading coefficient, so I know my end behaviors are going to be the same. They're either both going to be up or both going to be down. I have a positive leading coefficient. I have a positive 1. So what's it going to be? Up, up, or down, down? Up, up. Perfect. Start up, end up. Okay? It's going to look something like this at the very end of my graph. All right, C, I have an odd exponent, so I know that my end behaviors are going to be what? The same or different? Different. I have a leading coefficient of a positive 1, so what's it going to be? Start up or start down? Start down, end up. Okay? So again, I have no idea what happens in here. I don't know that yet. You will by the end of today. Okay? But we know our end behavior. All right, any questions on end behavior or leading coefficient tests? Okay. Let's talk about zeros. Okay, so copy in this little next part, and we're going to add some notes to this as we go. Okay, we're talking about zeros of polynomial functions. Now, you know another word for zeros. What else did we use to describe zeros? What did we call it? You remember? Yeah, x-intercepts. Okay, so zeros are another word for x-intercepts. Okay? Now, that word at most that I underlined in red is super important to us. Okay? Because what that tells me is the function could have at most n or it could have less. It doesn't have to have n. It could have less than n. But it can't have any more than n. Okay, so I'm just going to write a little note there. So it can have n or less x-intercepts. Okay, it can have n or less. The bottom part is talking about turning points. Okay. Now, I think turning points are easier to understand with a picture. Okay, so here I have, here's a picture of a graph. Okay, so here's one spot where things turn. I was going down and then I start going up. Here's another turning point. Here's another turning point. Okay, so in other words, this graph has 3 turning points. Okay? If it has 3 turning points, let's go backwards. If it has 3 turning points, what do we think its exponent could be? What's the lowest exponent it could have? Kind of go backwards. Not 3. If it has 3x, how many turning points? What's its exponent? 4.
I said 4.
Okay? Oh, I thought you said 3. 4 minus 1 gives me 3. Okay?
Yeah.
All right, so we'll talk about that. We'll see how that comes into play, I think last actually today. All right, any questions on these little bit of notes? All right. This little box up at the top is just what we just talked about. Okay? Now, let's talk about finding this algebraically. Okay? This is where things start to become a little more difficult. Okay? So it says find all real zeros of f of x equals negative 2x to the 4th plus 2x squared. Then determine the number of turning points. okay, and graph the function. So, first step, we have to find our zeros, or our x-intercepts. How do I do that? How do I find zeros? We just did it on our test yesterday. We plug in a zero where? For what value? Not x. Yeah, the y, the f of x. Okay? So, I'm going to plug a 0 in for my y, in for my f of x. Okay? Now, this is where factoring comes back into our worlds. Okay? So, we're going to factor this. I'm going to factor this by taking out a GCF. So, I'm going to take out a negative 2x squared. Always take out a negative. If you have a negative in your leading coefficient, get rid of it. Okay, so I'm taking out a negative 2x squared. So I have left over an x squared minus 1. How can my parenthesis factor? How does this factor into two separate parentheses? Awesome. X plus 1, x minus 1. Bring my negative 2x squared down. And my 0 down. Okay, so all I've done so far is factor. Any questions on how I factored these? Okay, now this next part. I know it's going to seem silly for me to write it all out, but I want you to follow along because you'll see why we're doing it in a second. So our first factor, negative 2x squared equals 0 is one thing I have to find the value of x for. X plus 1 and x minus 1. Okay, so 3 different values for x. Okay. So my first one, divide both sides by negative 2. I have x squared equals 0. I'm going to take the square root of both sides. And now this is what seems silly. We have a plus or minus 0. Now, does that make sense to have a plus or minus 0? No. However, we have to think about it now. Okay, and we'll come back to that in a second. But do not ignore this plus or minus when we take a square root, even if it's of 0. Okay? The other ones are a little easier. Okay, we know x is negative 1 and x is 1. Okay, no square roots there, so we don't have any plus or minuses. Okay, now here's why I bring up our plus minus. Because we have to consider multiplicity, is what we call it. Okay, multiplicity, meaning sometimes our graph can hit our x-intercepts more than once. When we have that plus or minus, that's really saying that I'm hitting 0 2 times. So we would say I have my x-intercept of 0 has a multiplicity of 2. Okay, my graph is hitting it twice. We won't necessarily see that on the graph, but we know that happens algebraically with the plus minus, so we have to account for it. Okay? Now my other two, I don't have a plus or minus there. Okay? So it only has a multiplicity of 1. Multiplicity of 1. Okay? Meaning it only occurs once. All right. Any initial questions on that? We're going to talk more about this problem. Okay. Let's go back up to the very beginning because I kind of ignored what we just did in our notes in the box above with our little rule here. Look at my leading coefficient. I have a leading coefficient of 1, which tells me I had at most how many x-intercepts? What did we say? Our rule on the last page. I had an exponent of 4, so how many x-intercepts could I have had at most? 4, right? Okay, I really only have 3 points that are going to show up on my graph. One of them is multiplicity of 2, but I still only have 3 points on my graph. How many turning points could I have at most on this graph? Oh, wait, no, yeah, 3. Sorry, you're right. 3. Yep, because it was 4 minus 1. Okay? So turning points. In fact, let me write maximum turning points, because we don't know for sure. Yep. The max number of turning points, as long as you know what it means, would be 4 minus 1, 3. Okay? Okay. Any questions on that one? Now, we're actually going to talk about this in terms of our calculator. So go grab one of my calculators. Okay, if you don't have one already. I have the steps on the board. Okay, I kind of crossed off the steps they give because that was like for an old situation. So an old calculator, we're not going to use those steps. Okay? So on our calculator, you're going to go to the y equals button and type in our equation. Okay, our negative 2x to the 4th from up here. Okay, you're typing in that equation from the top. Okay. Then you'll hit graph. Then second, and then the trace button. The trace button is one of those tiny skinny ones at the top underneath the screen. They're yellow. You're looking for 0, right? Because that's what we're calling these, the zeros. Now, step 5 is weird. I said follow prompts. Okay? If you look on your calculator, does it say the top or bottom? Oh, the bottom. See how it says left bound? So what that means is, when I look at my graph here, for example, I can tell there's going to be a point right there. I don't know what it is yet, but I can tell that there's a point right there. When my calculator says left bound, you've got like a little X cursor. You can go anywhere to the left of that point. So you'll use your keys, you'll hit enter. And then it'll say right bound. You're going to pick anywhere over here, hit enter. And then it says guess. You can just hit enter again. You don't actually have to guess. And it should move your cursor right to that point. Okay? Now that only gives us this point. So you'll have to do this step 2 more times to get the other ones. Okay? We're not going to do all 3 of them, but that's how you do it on your calculator. I don't care how you do it on your test. Okay? So some people will choose this way because it gets them all 3 in one go. Okay? We're not going to dwell on this because I'd rather you know how to find it algebraically. But here you have the steps. You can play around with it later if you'd like to learn how to do it on your calculator.
Where's follow prompt?
Where's what?
Follow.
So there is no follow prompt. So did you go to zeros, second trace, and go down to zeros? Hit enter. See how it says left bound? That's where you're going. Okay. Does everyone have the steps down so I can move away and you can practice this later?
I do.
Okay. All right. Now, this is really wordy, but I want you to read it. Then I'm going to talk about it. Okay? It's really wordy, but it's going to help us out big time as we start to graph these polynomials. So go ahead, read it. I'll give you like 2 minutes, then I'm going to talk. Yes. Best day ever. Thank you.
I don't know why I should have said that.
I really don't care at all. Just
We should be reading a paper, not a phone. Okay, so let's put our phones away because this is where I'm going to lose some of you, guaranteed. So now we're kind of putting things together. So this is where multiplicity is going to come into play. Okay, I brought it up last time, but we didn't really use it. Okay, here's where we're using it. Okay, so a factor, now we have factors of binomials. Okay, which is this set of parentheses of two terms. My exponent being k. Okay, if k is bigger than 1, so in other words, if I actually have an exponent, okay, that's written, it's going to yield a repeated 0, meaning we have a multiplicity higher than 1. Okay? If k is odd, if my multiplicity is odd, then we know at that point in the graph, it's going to cross at the x-intercept. Okay? If the multiplicity is even, then it's going to just touch the x-axis. It's not actually going to cross there. So let me draw a picture. I think it'll help. Okay? So here's the first example. Okay? Let's say it crosses here. We have a multiplicity that's odd number. We know my point in the graph here, it's going to actually go through that on the graph. Versus, if we have a multiplicity that's even, we're just going to touch there and keep going. Okay, so we don't actually cross. We touch it, but we don't cross it. Okay, do we all see the difference? So this is why we talk about multiplicity. Multiplicity tells us what happens at the x-intercept. Okay? All right, so let's just look down here. This example here, I wish there was some more space here. So write as tiny as you can, maybe be as organized with arrows as you want, okay? It helps when we see this example, okay? So for our first one, I'm just looking at our first term here. You're going to have to bear with me while I highlight and change my pens, okay? So x to the fourth. X would equal 0. That's my x-intercept. Because it has the exponent of 4, it has a multiplicity of 4. Okay? Because I'd be taking the fourth root of it. Now the multiplicity is an even number, so that tells me it's touching the graph here. It's not crossing it. Okay, Okay, so I would say you can write underneath like touching, or you could just write a T. Doesn't matter. I know I have the ability to write a little smaller because I can zoom in. So do what you need. But that's what we know just from that spot of my equation. All right, our next one. Okay, the next spot here. I know x is 1, because whatever it would be would have to equal 0. It has an exponent of 2, so I'd be taking the square root. So it has a multiplicity of 2. That's an even multiplicity, so I know that it touches here. Okay, it doesn't cross, it just touches. Okay, the next one, my blue one now that I've highlighted. Okay, the blue one. I know x is -2. That's my x-intercept value. It has a multiplicity of 3, because I'd be taking the cube root of it. That's an odd multiplicity, so I know that it crosses here. Okay, let me switch colors again. 2 more. Here's my next one. This one would be x equals 4. My exponent's a 1, so I have a multiplicity of 1 here. That's an odd multiplicity, so I know that it crosses. Okay? And last but not least here, we have our final one. I know my x value is negative 3/2. Oh, I need a negative in there. Negative 3/2. It has a multiplicity of what? 5. And it's odd, so I know that it crosses. Okay? All right. Any questions on that? Again, we're just kind of memorizing patterns. That's all this really is. Memorizing that, well, if I have an even or an odd, that tells me if it's going to touch there, kind of touch and bounce back, or cross. Okay. So now we've talked about end behavior. We've talked about zeros. We've talked about turning points. Now we're going to put it all together and sketch a graph. Now, it's sketch. Okay, because it's not going to be foolproof. It's not going to be 100%. But we're going to use all the pieces that we've talked about today. Okay? And I've given you steps. So the first step is apply the leading coefficient term. What else did I tell you that leading coefficient term was really talking about? What were we finding when we used that test? I think you said, what did you say? Yep, end behavior, right? End behavior. That's really what that test means. So first, make sure our equation's in standard form, meaning my highest degree polynomials is first. Okay? So here's my leading coefficient. My exponent is even. What does that tell me about end behavior? Is it the same or different? The same, because it's even. So it's either up, up, or down, down. I have a positive 3. So what does that tell me? Is it up, up, or down, down? Yep. Start up, end up. Okay? Start up, end up. Now, I would not recommend. Does everyone have a pencil in here or something they can erase with? Okay. So, as we start to sketch this, don't write in pen or something that you can't erase. Okay? Because as we sketch, we might need to go back and adjust a few things. So right now on my graph, we know I'm going to be up, up. Okay? I know my end behavior already. Okay? All right, so that's our leading coefficient test. Next part, finding the zeros. So again, I'm going to come up with my equation here. I'm plugging a 0 in for what again? The y. So I have 0 equals 3x to the 4th minus 4x cubed. Okay, and now I have to factor this. I'm going to take out my GCF. What is my GCF of these two terms? X to the 3rd. So I'm left with just 3x minus 4 on the inside. So now let's talk about what we just did with multiplicity. Okay? Once you have it factored, you're ready to think about multiplicity and what happens at each x value. So this first one, I know my x-intercept is 0. It has a multiplicity of what? How many times is it going to appear? 3. That's an odd multiplicity, so is it going to cross here or touch here? Cross. Perfect. All right, our next one. I know my x value is going to be 4/3. It has a multiplicity of what? Just 1, right? Because I have an invisible 1 right there. That's odd, so I know it's going to cross there. Okay, so that's everything that we just did on the last one. We did here. Okay. So now let's graph our 2 points that we just found. So we know we have an x-intercept at 0 and at 4/3, so like 1 1/3. Okay, so those are our 2 points where we're going to cross. Now, here, don't write this. So I'm just going to show you our next dilemma here. Okay, again, don't graph this. I have no idea if I'm going to cross like this or if it's going to go like this. I don't know. Okay, I don't know that. I know that they cross there, but that's all I've got. So step 3 is crucial because it helps us determine how many turning points we actually have. Okay, we're going to plot a few additional points. Now we pick them strategically. Okay, you're always going to want to pick some points in between and around our 2 x-intercepts. So I'm going to pick a point in each of those pink highlighted spots. Pick some nice ones. So, for example, I think I'm going to pick -1 because that's right there. I'll pick 1 and I'll pick 2. Okay? Pick some nice ones. Don't make your life miserable. You can do these one of 2 ways. Okay? You can type your equation in your calculator and go to the table. Or you can take each point and plug it into our original problem up here. Okay? So I'm just going to write out the first one so you'd see what we would do in our calculator. Okay? So that's what you could do. You could do it by hand, or like I said, you could just put it in your calculator and find the table of values. I'm going to give you our numbers just for time's sake. We would get 7, -1, and 16 would be our y values. Okay? 7, -1, and 16. All right, so now, again, this is just a sketch. So I know -1, 7 is a point. So I'm going to go -1, 7, and it's like up here. It's actually off our graph. Okay? -1, 7 is just about there. 1, -1, and then 2, 16, which is like way off our graph. So I'm not even going to graph it, but it's like way up here. Okay? So now this is why I told you to be careful. Like you might need to erase. Because right now I know I'm going to need to adjust my end behaviors. I put them too far apart. Okay? But I know that my graph is going to come down and it's going to finish up like this. Okay? That's my sketch. Doesn't have to be. That's just at most what it could be. Okay? All right. Any questions on sketching this graph? All right. You have about 5 minutes until lunch, so I want you to start this next one. Okay? When you come back in from lunch, I want you to keep working on it. We'll go over it about 5 or 10 minutes into lunch. Now, before you start, look at my equation. I have a fraction. How do you get rid of a fraction again? Yeah, just multiply by the denominator. Okay? Now we need to multiply everything by that. Okay, we need to multiply everything by that. So I would have -4x plus 12x minus 9. Now, I wrote the 0 here because you're really only going to need to use this when you get down to the finding the zeros part. Okay? And I'll tell you right now, this is a difficult factoring one. Okay? Accept the challenge, try it. Okay? It is a harder one to factor, but I want you to see what you can do. Okay? All right, you guys can go ahead and start working. You got 5 minutes till lunch, and then you'll pick up when you come back.
All to the left and right, what does that mean?